Okie dokie. So on to number 2 on the practice final exam. And um, this one would have been 7 points, probably like maybe probably a breakdown of 2 points, and 3 points, just in case you were wondering about how that would usually go between parts A, B, and C. Now, if we're looking at the diagram, we got 4 electromagnets, 1, 2, 3, 4, on the stator. Each pair of electromagnets receives a different phase and is connected as indicated by the numbering. Okay, so in other words, we've got like a pair of electromagnets that would be receiving power from phase number 1, like that. And I guess we would have to sort of make sure that we complete the circuit. And then the second phase would be connected in a similar way, albeit, to some different source. Or there'd be some sort of game, more likely anyway, would be some sort of game was played like putting a capacitor into the branch of the circuit with this second pair of electromagnets in there, and that would split the phase of a single AC source. But it doesn't really matter for this problem. We just know that we're getting 2 phases, and they would form 2 sort of separate circuits. Okay, so but the first question, what type of AC motor is this, and what is this type of rotor referred to as? Okay, so the type of rotor, we really only talked about 2. There's either fixed pole rotors, like with a permanent magnet, or like an electromagnet that we would have to run a brushed connection to. And then there's this kind that we're looking at here. And here we're looking at the cross-section of it. So these would be like the individual bars. And we're looking at the cross-section of them, so sort of down their length. And down here is sort of a side view of it. And we've seen this kind of diagram in lecture. So we know that this type of rotor is referred to as a squirrel cage rotor. And you generally see those on induction motors. Now there's different kinds of motors out there. There's sort of these hybrid ones where they use a squirrel cage kind of geometry on the rotor to get the motor up to speed, and then once it's up to speed, they have some like an electromagnet that takes over, and so they can run it at the synchronous speed, and there's all sorts of tricks you can play, and there's lots of different, a lot of wiggle room and bleed over between the categories of motor, but we're just sticking to the main categories here, and that's what we've got. All right, so part B, if this motor has 0 mechanical load on the rotor, what would its speed be in RPM if the input had frequency equal to 50 hertz, like they do over in Europe and various other parts of the world? Okay, so remember that the speed of an AC motor is, well, at least at synchronous speed, so the speed of rotation of the magnetic field around the stator, which the rotor is sort of trying to follow, is mostly dependent on the frequency, and then of course dependent on how many poles and how many phases we've got here. So if you go back to your equation sheet for the practice exam, you'll see an equation that looks something like this. Nice plane going by overhead. I don't know if you can hear that, but I got the window open because it's warm this weekend. It's nice. I get to spend it inside working on final exam stuff. Good times. All right, so we've got our equation, poles per phase on the denominator, and 120 times the frequency of the input on the numerator. So if we just plug in all of our quantities, we get 120 times 50. We have, remember, our definition of poles means that we can just sort of count up the windings. So we have 1, 2, 3, 4 windings, so we have 4 poles. And we have 2 phases, as we've already discussed. So the whole denominator is just 4 divided by 2, 2. The numerator is 6,000. So 20 times 50, 1,000. 100 times 50, 5,000. So 6,000 in the numerator. and 2 in the denominator, and we get 3,000, move over here, RPM. Okay, and that would be the speed that the motor would rotate at if we actually had 0 mechanical load. In practice, you never have this, because even if the motor isn't connected to anything, it still has to overcome, you know, the resisting torque from the friction in the bearings and things like that. But theoretically, you can get an induction motor to rotate at the synchronous speed if you have actually 0 mechanical load. Okay? So, moving on to part C. In practice, this motor requires a difference between its rotor speed and the speed found in part B to exert any torque. What is the difference in speeds called, and why is it required to create torque? Okay, so the first part of this, what is it called? It should be easy for us, for you, and for me. Slip, right? It's called slip, and that's the difference between the rotor speed, how much the rotor speed lags the synchronous speed, okay? And remember that we need that difference because otherwise we don't have a changing magnetic flux or a changing number of magnetic field lines through the squirrel cage. And if we don't have that, then we don't induce current. And if we don't have current in our magnetic field, then we don't get any force and thus torque on the rotor. So let's write that out in some form here, okay? So slip, no slip means no changing magnetic flux or number of field lines, okay, in the cage. So no induced voltage and thus induced current. No current, no torque. Okay, so you can state that in a lot of different ways, but that's a reasonably concise one. So no slip means no changing magnetic flux in the cage. So no induced current, no torque. So you can get away with that, and that's reasonably complete. Sort of shows the whole chain of logic, tells me that you're understanding sort of what the fundamental reason for slip is, and that would get you 3 points. All right, so that is where I'll cut off. We're coming up on 8 minutes for this video. We probably could have, go on and do question 3, but I'll just chop it up and put it in a different video. It's also breakfast time here, so I'm gonna go do that, and then I'll be back and posting these later today.